Hello, it's David. I'm back looking at my Falcon power supply. If you recall last time, I recapped it with a kit from Exos, and we got some lovely grubby, particularly crusty capacitors off it, but there was one missing. It turned out that unfortunately one had missed the packaging. Well, the Exos store fairy has come straight back to me and has very kindly sent me the missing one free of charge. So it's time to whip off my temporary fix, the purple one there, and put this one on, and then we'll do some follow-up measurements on the oscilloscope under load. So let's get on with it. So the capacitor in question is a 25 volt, 680 microfarad, 105 degrees C electrolytic, and I can't remember what I squeezed in there last time, but it was reclaimed from an old ATX power supply, so it's clearly not going to be perhaps an improvement over the near 30-year-old one on there, but it's clearly not going to be as good as this. So let's whip that one off and get this one back on. Change my soldering iron tip for my preferred through-hole spade connector. And I'll get that heated up to about 300 degrees. Now, because I don't like testing this when it's exposed, I've made a little case to sit over the power supply when it's all assembled, stop fingers getting poked in, and let us do some testing. The case has a gap for the connector to go through, and it just is secured in opposite corners with the normal screws. Difficult to get your fingers in here. Difficult to get your fingers in here. I may need to cut a little slot there, but otherwise I suspect that would actually fit inside the case. So last time, in my first video, I used my electronic load to test the 5-volt rail, didn't test the 12 at the same time. Now I realised afterwards that the whilst this is a linear regulator in here and should be noise free, my automotive voltmeter that I'm using there to measure the current across the current sense resistor is noisy, very noisy as it turns out. So most of the ripple that I was seeing on my oscilloscope waveform I think was backfed from that voltmeter. So I'm going to not use that one this time, and instead I've got here a couple of Wirewound resistors. So I've got a 12 ohm 25 watter and a 2.2 ohm 25 watter. So this one basically should pull somewhere in the region of 2 amps on the 5-volt line, and the 12 ohm one should pull something in the region of 1 amp on the 12-volt line. Mount them to a bit of wood because I don't really want them flapping around and burning me. They will get hot. I know they're rated for 25 watts, and we're going to be putting through sort of 10, 12. So there's a fair margin there, but they still warm up. So what I'm going to do is test both lines at the same time. Ground. There we go. Right, so that's interesting. 1.7 amps, that's dropping down to 3.7 volts. Now that is considerably below specification. The 10.5 is less important, but that's still low. 3.7, that's not going to do anything. So I'll need to actually check the spec for the Falcon's power supply. See whether I'm overloading it. Nevertheless, we can still measure the ripple, which is what this was all about in the first place. Remind me to get a new multimeter. Okay, so this is the setup we're going to use to test it with. We've got the 5-volt rail, ground, and the 12-volt rail. The 12-volt line goes through the 12-ohm resistor and returns to the common ground point. The 5-volt line to the 2.2-ohm resistor and returns to the common point. And we've got our oscilloscope probe attached here to the 5-volt rail with, again, the ground coming to the common point. So first of all, no power on, let's take a look at the background noise. So we've got the probe here in DC coupling mode, and you can see there's bursts of noise across here. This is at the 200 millivolt level, 100 microsecond time base. So we can adjust our trigger level. You can see if I bring it up to 64 millivolts, there's a sort of packet of noise, and that's maybe to be expected. This is a particularly electronic noisy environment here. I'm out in my shed. We've got Wi-Fi, we've got lots of different computers, we've got hard disks clattering away, and we've got power line Ethernet. So perhaps not unsurprising that we're seeing packet style noise when everything is turned off. The mains is not plugged in at all, so we could try to plug that in and see whether earthing it makes any difference. So that's with the ground plugged in, and perhaps there's a slight reduction there, but generally there's going to be some noise imposed on what we're sampling here. So if we move our trigger level up a bit more, there'll come a point where we'll see fewer triggers events. Okay, that's a bit rarer now. Here we go, we're getting up to 160 millivolts. 176 millivolts, it's sat at weight. There's a couple, there we go. So infrequent bursts, and that's at 200 millivolts of vision, and we're seeing the occasional one just exceed that. So we're looking at around a 200 millivolt maximum noise when off. However, let's take a sort of centroid figure, so where we're seeing the edge of that boundary, which is about, let's say there we're getting quite a lot of feedback. So that's about 140 millivolt in one direction. So let's say 300 millivolts peak to peak for the bulk of the background noise. And there's always going to be some exceptions. So we're in DC coupling. We're going to need to switch to an offset of 5 volts here. Let's put our trigger level. Well, first what we'll do is we'll put our trigger into auto, so that we see what's happening. And I'm going to crack the position down to minus, probably say around the minus 4.9, because we saw there was a bit of a voltage drop let's power it on. Okay, so power's on, nothing's smoking. Oh, I'm in stop mode. Ah, and there we go. So let's just have a look at the voltage there. So what's our Vmax and our Vmin? So we're getting, oh, there we go. Floating around the 5.2 max and a 4.7 min. So about a 0.5 volt peak to peak, to be honest. And the noise characteristic is here now, it's obviously very, very different. But we can still adopt our same approach. I'm bringing the trigger up here. And let's now take the trigger up beyond 5 and see where we start to see. I'll need to switch, sorry, the trigger mode back to normal. Start to see where we get that drop off. Slowing down, 5.25, 5.26, 5.3, just the occasional flicker. 5.3. So that rules out most of the outliers, and we can see that centroid figure is around, well, there were consistent peaks about there, so I'm going to say that's what's 5.15. That's a little high. And we can obviously do the same trick in the opposite direction. .6, everything gone. 4.62. There we go. On the edge there, about 4.65. Okay, I can smell the resistors are starting to warm up now. So just out of interest, does that figure look any different if we disconnect the 12 volt rail? Not really. So the lack of load on the 12 volt rail doesn't seem to have much effect on the 5 volt. So let's lengthen the baseline a bit by winding in the time base. And here we can see a few more peaks, so let's have a look at our peak to peak figure as well. So we're getting that occasional burst up there to half a volt, which is the noise we were seeing before. So to be honest, I think we're at the limit there of what we can realistically measure in this environment. But there's nothing particularly egregious going on. I don't have any concerns that this is going to now blow up my Falcon. If anything, I'd be a little bit worried that the voltage level is too low. So I'd be happy now to put that into the Falcon and give it a test. But I think the key thing is going to be now measuring the voltage from that 5 volt rail once it's under load. So I hope that was interesting. Thank you very much to Exos for replacing that capacitor. I now have a fully recapped Falcon power supply, which I can use now to test my accelerator cards.